So, everybody, welcome back to Codeforces, and now we'll talk about the actual implementation of segment tree and other data structures that work with range queries. Let me open the screen. Okay, so we have 6 problems for today. First of them is naive RMQ. We give an array of n elements, and we have only queries of the form LR, which want us to find minimum elements of A with index from L to R inclusive. And there are no update queries. So because there are no update queries, you are completely fine with finding minimum with a simple for loop, or in this case, I use std_min element, which is from algorithm, that takes in 2 iterators. So I just get the first element that I want to check and the last element, and I just ask like library function to find the minimum element in linear time. And because there are only 1,000 elements and only 1,000 queries, I'm completely fine with it. And the point is that sometimes, despite the problem is stated like range queries, it may not require you to actually like use some advanced data structure to process these queries. Sometimes you are completely fine with just a for loop. So always watch out for the constraints. When constraints are low, you don't need to search everywhere for your segment tree template. You can simply write a for loop, or you can use STL if you know so. So yeah, this problem has rather educational value, that you don't have to overcomplicate the problem. Like, no matter how short my segment tree template is, it would take more space than like 3 lines, right? And I can put this here. I just wanted to make it more explicit. So we have like, we explicitly take the iterator. May as well make it const, just in case, you know. So yeah, sometimes you're completely fine with a for loop or a call to library functions that does something in linear time. You don't always have to use segment tree whenever you say range queries. And it's important not to actually, because it saves a lot of time. Like I can write these lines in like 30 seconds. And if I copy paste segment tree, and then I just type its methods to compute the same thing, I believe it will take like at least 2 minutes if I have exactly the correct version of segment tree pre-written. If it was some other function, like for example, XOR, right? I don't have segment tree pre-written for XOR. You know, I would have to modify my segment tree, or maybe I would need to like write an explicit combiner if you use a segment tree with lambda functions or functors. Well, either way, like it would be slower than just typing this. That's exactly why like I try not to overcomplicate the problems that I solve, especially in this series. So that's it for that problem. The next problem, and I want to talk about this problem next because it's the simplest one. Given an array of n elements and you want to answer range sum queries. Here actually array is long and you have 100,000 range queries, but there are no update queries. So as we already talked about, you can just use prefix sums to answer this kind of queries. And like way to do it with STL, you of course can write a for loop, but you can also say like, hey, prefix sums equals 0, and then use partial sum with back inserter, which is from iterator header. It will fill this vector with prefix sums for you. And because I use int64t like long integers here and here, it will not overflow. So you don't have to think about it if you compute by hand, then you would have to think about it. But here, like you explicitly write in 64T once, and then you're fine. I'm not sure whether or not you need to write in 64T here, but either way, like again, just use prefix sums when you can. Again, it takes 3 lines, this 3 lines. And it's just faster than copy paste and segment tree. Especially if I were to use variable names like PR minus P L minus 1, and if I did not put spaces, then it's clearly faster than copy paste and even segment tree. So do not overcomplicate your problem. So when you see like you don't have to be particularly efficient on range queries, you can. It most probably means that you don't have to be particularly efficient because the difficulty of the problem is somewhere else. You don't have to worry about using segment tree when you have like 5,000 queries on the array of length 5,000. But sometimes you do want to use segment tree. For example, in problem B, we have some array which is given like by generator, not because it's particularly long, because they just did not want to have array explicit. So we have array that is generated in some fashion, and we have want to find the variation, which is difference between max and min on the segment, and want to assign 1 point assignments. And we can use regular segment tree for this purpose. So I have a class segment tree. What I initially did is like, I said like, I want this interface. I want range variation and point assign with from left to right with index to value. Right? And then for each method that I implement, I also want a private method that will take some auxiliary information about the tree, because we don't store the tree as like pointers, we store it as an array, as a vector of size 4 times the size of the original array. It usually takes less space, but just to be extra careful, we take 4 times size. And we do it by shifting twice to the left. So this will denote an index of vertex, of tree vertex that we're currently in. All these methods start with 1, 0, and size minus 1, which denote the like index of the in this array. Also, like what is the left position, what is the left endpoint of the segment that current vertex corresponds to, and what is the right position. So if you look at the implementations, they like these are simple wrappers for this. Just do this. Again, 1, 0, size minus 1, 1, 0, size minus 1. If you don't want your segment tree to be a class, it would just mean that you don't need these interface methods. You can just call explicitly with 1, 0, size minus 1 in your main program. But I kind of try to make like every data structure a class, because then it becomes more usable, I think. So, like these are simple wrappers. This is generation of the array, and here we actually answer queries just using the interface of the segment tree. How does it actually work? Like how to build the segment tree? Well, if your segment tree, if your current segment is 1 point, then you can just initialize whatever statistics you want to compute. In this problem, we want minimum and maximum, so we do exactly that. If it's not 1 element, then you want to split it in half. So you go to whatever is the middle in the tree. What is the ID of the left son is this, what is the ID of the right son is this. I believe you can write ID of the right son this way as well, because of the priority of the operations, but, operators, but I prefer it to be extra safe. And you can initialize left half, initialize right half, then you can compute the statistics. So minimum will be minimum of 2 minimums in children, and maximum will be maximum of 2 maximums in children. And you want to query for range variation. And when you want to like query and assign, you will have usually more else ifs. So if like for whatever reason your left endpoint of the segment that you query for is bigger than your right endpoint, then you want to return some like correct initializer, because the most compact implementation of segment tree, it does not check what queries it makes when it makes them recursively. It just queries for something. For example, here, maximum of left and 3 middle plus 1 can be 3 middle plus 1, it can be greater than right. But we don't want to check it here, so we only check it once here. On the other hand, like this base case corresponds to when your query segment is completely equal to your tree segment, then you can just return whatever is stored in this vertex. Otherwise, you make 2 recursive calls for left min, left max, right min, right max, and you compute the answer as minimum of minimums and maximum of maximums. When you want point assign, it's the same thing. When your interval is 1 element long, you just do your assignment. Otherwise, you do pretty much what you did in the build method. So this is completely identical to this. Oh, almost completely identical to this, because you only have to like recurse into one branch depending on what element you want to update. And you can find this code, this entire code on my GitHub. It's not like the best implementation of segment tree, but it's reasonable. And that's what I was after when writing it. So yeah. Now next version is when you want lazy segment tree, and you may want it when you want, like, here you have assignment on range assignments, right? Range assign and range sum. And again, we have these wrappers, and we also have push method. Now this still work in the same way. They're just interfaces for what is about to follow. This implementation is pretty much similar to what you already seen. So I won't comment a lot on it. Interesting parts are pushes and whatever and uses of lazy. Now lazy is like the buffer to store delayed changes. And push is the way to like push these changes to the children and then make them deal with it. So whenever you want to query for range sum, you make push of the current vertex because you want its state to be up to date. Whenever you make range assign, you also want to make push. Actually, I'm not entirely sure why you make push here. We may get away with push only here, but whatever. No, okay, we also want push for this case when we query for something. Okay. So it never hurts to make like constant number of pushes, right? Because we already analyzed the complexity of this operation. But I'm still a bit confused. I believe that somewhere here we don't need the push. Potentially we don't need that push. Yeah, I think that we don't need that push because like when we got here, we already made that push. So yeah, you can just make push whenever at the beginning of your every function. It won't hurt because we already included it in the complexity analysis. So now, what does the push do? If lazy has something to push, and the typical way to do it is like compare with some sentinel value. If lazy has some delayed update, if this is not one element update, then you want to push it to its children. When And then you want to update. So for here, for example, lazy means that we assigned one value to the entire segment. So how do we update sum? We take whatever is the length of that segment, make sure that it does not overflow, and we multiply it by it, and we get the sum. And then we say like, oh, actually we already processed that push, so there are no more delayed changes here. So that's an implementation of lazy pushes, and that's actually shorter than the previous one, because in this question we start with arrays that is initialized with zeros. We don't need initialize method, which saves a couple of lines. This is like, there are less than 100 lines of code actually, because there are a lot of empty space. And also, obviously, you can write tr, tl, tv instead of all these explicit names. I just write them because I know that people read my code on GitHub, and I want it to have reasonable variable names so that you can understand what we're talking about. So that's it for lazy segment tree. Like, things you have to be careful about. Just make push once in the beginning of every other function, and you'll be fine. It's included in complexity analysis, and so you will still have logarithmic updates. In queries, just make sure that it's implemented correctly. Like, for example, for minimum, we obviously want different like updater here instead of multiplying the length by the sum. So yeah, that's it for that problem. I might actually right now test that it is correct. So here is this. Just make sure that it's correct with the changes I made. I'm pretty sure that it's correct. Or actually, interesting, did I change? Lol, did I change anything? I was not expected to change. Because we changed the lazy value, we also want to push here. Yeah. That was important. Because we updated the lazy, we want to change. We want to push again. Oh, yes. So yeah, it's accepted now. So yeah, whenever you update lazy, your actual, or whenever you will query for the value, whenever you want your information to be up to date, you have to push. That's it. I believe we will fail without that push as well, just to make sure. Because that push may be important here. Yes, you can see so. So yeah, whenever we need information up to date, we have to push. Yeah, that's it for lazy segment tree. Next problem involves sparse tables, and sparse tables are extremely short. Like, there are only 60 lines of code for sparse tables for RMQ. This just allocates memory and initialize. For first layer, you can just copy the array. For all of the successive layers, you just say like, hey, sparse table at power first equals minimum of sparse table at power -1. This is the first half, then this is the second half, where second is first plus 2 to the power of k -1. Whenever you want minimum, you find whatever is the largest power that you can fit twice, that you can fit between left and right. And then you make this query and this query. which say, this is the query that ends at right. And like all this stuff is just generation of the queries and of the array. And you need it because you have, in this problem, you have 10 to the power to the 7th queries. So they can't give that huge input because you just won't be able to read it. So they give you a generator. So that's what I do here. And then they just want you to output the answer to the last query. So it's pretty unlikely that you will answer it correctly like after 1 million or 10 million queries if something went wrong, right? So yeah, that's it. We already covered sparse tables in our LCA video, and if you missed it, I encourage you to watch it as well, because LCA is another important topic if you want to get from div 2 to div 1, I believe. And the same about segment tree. Yeah, that's it for sparse table, I believe. They are as simple as this. This is actually the shortest program among these 6. So it is quite simple. And then the last problem is actually a killer here. It requires a trip. And I'm actually not familiar with what is object-oriented way to implement trip. I tried earlier today and I failed. So if you know how to implement trip as a class, actually I kind of know where I can watch for it. Yeah. I will just check some libraries of code people that I follow, and we'll be able to figure it out. But for now, I have implementations that's more like Olympiad style, competitive style that just has a couple of functions, and it's your responsibility to call them correctly. But it's actually quite simple still. I just have to call insert and range minimum. And this is a problem when you insert elements at some index and you want to, no, this is insert and this is minimum. And there is some explanation for you if you want to read like what is actually this means. They decided that this kind of problem is difficult, so they give explicit explanations. So I translated it as well. So basically when you're working with trips, you will have your split and merge always. It's more or less the same. And wherever you merge or split, you actually want to update some statistics that you maintain in trip. And update will just go to 2 children, ask for their stats. For example, here I maintain size and minimum. So size will get 1 plus size of left plus size of right. Minimum will get minimum of current key, minimum in left, minimum in right. So update statistics, assuming that statistics of children are correct. And they are correct if you use strip in the intended way. And range minimum from left to right, you split your trip at index left. You then split the second part at index right minus left plus 1. This way you actually get like whatever is less than left here, whatever is bigger than right here. And middle trip is exactly what you want to query. And then you can just query minimum here. And then you merge it back because you want to maintain one trip at a time, except for the specific moments when you query for substats. So you split twice, you get exactly the part that you want to query on, and then it guarantees that it maintains correct statistics in it. When you want to insert, you again split on the insertion index. You create a new node, a singular node is also a trip, then you merge it in just the way it was here. So as simple as it gets. Ability to split and merge is just overpowered. Speaking of implementation details, I have randomized priorities here. The way to achieve it, you can just write explicit constructor for your trip. that will generate random priority, random integer priority. I'm actually not sure whether or not you want to write this, but it's okay. And you just call like whatever your integer, whatever is your priority distribution, you call it from random number generator, you get your priority, which is random number. The only thing you have to watch for is that your generator is static, right? Because then it's only like one instance for all trips. Because this is a heavy object. And you don't want to define a separate generator for each entry, for each node. So you have to mark it as static or just make it global if you prefer this way. I don't prefer, so I make it static. So yeah, this way you will have one generator. It's still pretty random, but you save a lot of time constructing these heavy objects. So yeah, and it's also like because all of these functions, they work with pointers, it's common practice to define like pointer to trip and just use it all everywhere else, not to write like trip star reference, because like a reference to a pointer confuses a lot of people. That's actually like the way to have output parameters. Right, to have pointer as an output parameter. Nothing complicated here. So these are pretty generic. You have this implementation most of the time, and it deals with like several simple cases where you want to split and merge and how. And that's it. That's it. And you, of course, can have multiple other ways to work with range. Like instead of range minimum, you can have other stats. But it's not the topic of this problem. So before we end this video, I actually want to talk about some resources. So one great reference that I always use is cpalgorithms.com. If you have any sort of theoretical question, I suggest this as a reference. For example, this article about segments trees covers a lot of like standard cases. I only told you about like a couple of cases which in fact cover like every significantly different usage case, but do not cover all usage cases. So you may find it useful if you want to read more about it. And it contains a lot of algorithms, data structures. And you can just list through, but I just use page search. So Sparse Tables, they have like even shorter implementations in mind. Yeah, just really short. But again, I prefer to be in a class, so it's more usable. For example, I can have multiple RMQ data structures in the same program, in the same scope. So yeah. It also has trees. And all of these articles are pretty good. They are translated from an old Russian resource. They have usually shorter implementations, but these are sometimes difficult to understand, just sometimes. And by the way, you can build trip in linear time, but it does not matter, usually. There are some usage cases, there are some practice problems. If you want to practice more, you can definitely solve this. You can test your implementation. And overall, it's just a great reference. Yeah, again, if you know Russian, yeah, it's translated from this resource, emax.ru. It It was developed like back in 2010, 2012, I believe. Here you can see the log of changes ends at 2012. It's still very, very, very up to date, I would say. So yeah. I just wanted to show you it because often people ask like, where do you find all this information that you share with us? So partially I find it here. And if you're looking for more practice, there is another Codeforces gym. Let me quickly find it. By the way, if you're using Codeforces in English, as I assume you are, search for this thing, although you not really can search, but here there are all like problem sets that I translated. This all, as you can see, I solved everything here. So yes, these are all our videos. You can't really search for it because you don't have Cyrillic keyboard, but if you had it, then you would be able to search like this. But if you search in Russian for the same thing, and you will see that there are many more topics. I solved a lot of them, but I definitely did not solve all of them. And there is a second part about range queries in segment tree. Like with some difficulties, you can translate these problems yourself. I will cover this soon, but not today. Okay, so give me a couple more days and I will solve all of these problems and we'll talk about them like a bit more advanced range queries. And beyond this, there's like a limited number of trainings. I hope that at some point I'll translate them all and I will solve all of them. I believe that solving like half of this already makes you a grandmaster, to be honest, because it's just so powerful. They have a separate training on trips only. Like range minimum is just feature trip, like as a side note, but there are like 4 more problems specifically about trips. So yeah, solving this, despite they are 8 years old, you can still see a lot of activity going on. If we head on here, let me just change it to English so it does not look all that strange. If you got the status, you will see that I was solving a lot of problems today, but just like yesterday, some people were solving the problems. Also like massively, right? So maybe improving the implementation or testing different versions. Right, so this is sparse table, but everything else is pretty reasonable. And this is trip. So yeah, trips are solved because of pointers. Sparse tables just take a lot of space. Other than that, segment trees, like lazy segment tree, pretty safe from time limits. Standard segment tree. This is prefix sums actually. So yeah. These problems are good because they have tight constraints. So if you do something like it has an extra log factor, you won't pass. It's cool. Yeah, people solve it still. People still solve it. As you can see, like there is still some activity in Python and PyPy even. And it's unfortunate that you rarely can solve these problems, all of them in Python, because constraints are pretty tight. So it's like for really competitive people who write only in C++. And as you can see, like if you're looking for English statements, they are here. They link to my GitHub, just in case you were wondering. So that's pretty much it for the implementation part. Let me just quickly. I believe that there is one more thing. It may be interesting. There is such thing as headquarter library, and I did not explore it a lot, but there is such thing like lazy secretary. Which is, yeah, it's much better than my implementation because it's much more generic. But at the same time, you kind of have to understand what exactly is going on everywhere. So yeah, if you're interested in like super overpowered version, it can do everything, and you're most probably interested in like headquarter library. Because my secretary is by no means generic. I'm not ready for that stuff yet, I believe. It will try to borrow some stuff, for example, I will try to borrow mod int. Because it's just very, very useful. I don't think I will need this. So yeah. I will definitely try to borrow this, or even better, write my own implementation for this kind of thing, because it's just very useful. So yeah, if you're interested in like this kind of stuff, you can read other people's code and just select whatever works best for you. It's another great way to improve your skills. So yeah, that's pretty much everything that I wanted to talk for today about implementation of different data structure that can answer range queries. If you have any more questions left, you can always read my code, and you can always join my Discord server and ask me questions there. So yeah, thanks you all for watching. If you enjoy this kind of videos, you can always share it with your friends if you're interested in competitive programming, because learning together is often much more fun than learning alone. Like partially the reason why I do everything on camera is because it makes me feel like much more like a part of the community, and I just got to know that many cool people because of it, so I'm super happy with it. So definitely practice together with your friends. Don't think about it like it's a competition between you and your friends. It's not. It's like really a competition between you and problems, or in the worst case scenario, between you and like people from, I don't know, from different country, but definitely not with your friends. So learning together is just much more fun. So yeah, thanks you all for watching. Hope you enjoyed. If you do and you want to see more such videos, you can always subscribe. I don't usually ask for it because like you know best what's best for you, but yeah, definitely helps, and you get to know more people if you do subscribe. So yeah, that's all I wanted to say for today. Again, thanks you all for watching, and see you next time with more, I believe, segment 3 problems on, let's say this video comes out on Wednesday, and like around I won't say the specific time because it's different in different time zones, but I believe that on Thursday I'll be able to release the second version. So yeah, see ya. Bye bye.